Okay, welcome back everyone. We're going to continue our discussion of circuits, of DC circuits, by talking about some of the similarities and differences in series and parallel circuits. So we're going to start by just drawing a simple circuit. And one thing that you might want to do is to start with the battery and then follow along a closed loop starting with the positive and draw what you see. So at the top, we just have a simple circuit with a battery and a light bulb, and sometimes a light bulb is a circle with an X through it in a circuit diagram. And then at the bottom we have two light bulbs, a switch, and a battery on the left here in series. And on the right we have a battery and two light bulbs in parallel. So notice the basic idea here is that in series they come one after the other. So the World Series of baseball is because game 2 comes after game 1. And so in parallel, you have two things occurring essentially at the same time. So we'll talk a little bit more about this in the next slide. Okay. One thing we want to talk about first, though, is the role of the voltmeter and the ammeter in a circuit. So voltmeter is represented with a V, and the ammeter is with an A in a circle. And the way that we want to put these in a circuit is that they have to be put according to their definition. And so basically an ammeter, because it measures current, has to be put in series with the current that we want to measure. So we want the current to flow through it. And the voltmeter has to be put in parallel with the voltage that we want to measure. So it has to be placed across the device. And that way you can measure the change in potential on either side. And another thing is that, as we'll see, when we put things in parallel, we have the same voltage through the voltmeter as we do through the resistor. So it gives us a pretty accurate view of what's going on. So current goes through the ammeter, and the voltmeter is drawn across the resistor. Okay, now one last thing to point out is that an ammeter, we usually want to have an extremely low resistance, and a voltmeter is typically going to have a very high resistance. And we'll talk a little bit more about this when we get to some of the characteristics of the different types of circuits. And so here are the two basic ideas, that a series circuit is one after the other, and parallel is between a set of junctions and parallel to each other. So first we have an example of a series circuit where you have three light bulbs one after the other, and the parallel is between a set of junctions and parallel to each other. So for example, this and this would be two junctions. Okay, so actually there's two sets of junctions, and any current that comes into this junction has to decide whether to go through the light bulb or to continue onwards, and how much current does so is usually determined by the individual resistances of the light bulbs. And so we'll talk a little bit more about this math in a moment. Alright, so we have a series circuit, and so they're wired one after the other. They experience the same amount of current for the same reason that when we had capacitors in series, they had the same amount of overall charge. So this is just the charge on each capacitor. Charge is conserved in series, and throughout these lessons we'll be referring back to the phrase CSVP, which means that charge or current is conserved in series, or is the same, and voltage is the same in parallel. So that's what CSVP means, and we'll come back to that many times. So in this circuit, you can see that there's three light bulbs that are between one end of the battery and another, so they all have the same current. So I is equal to I1. So if this is I coming out of the light bulb, or out of the battery, sorry, we have I1 through this first light bulb, I2 through this third, I3, but they're actually all equal to just I. So whatever goes into one light bulb must come out and go on to the other one. So it makes sense from a conservation of charge standpoint that the charge just goes from one terminal of the battery to the other. The voltage, however, is going to add up. So the voltage difference of the battery will be equal to V1 plus V2 plus V3. And one analogy to think about this is that it's kind of like a bus route. The bus picks up V number of people at the station, and there's different stops. And by the time the bus gets back to the station, hopefully everyone's gotten dropped off. So some of the electric potential is used in the first light bulb, some is used in the second, and some is used in the third. Another way to think about this is if you just think back to capacitors, and resistors have this as well, so light bulbs, it doesn't really matter which way you go with this, but there's an electric field that is going across each of these resistors. So there's an E field which is going the same direction as the current, because the current is the motion of positive charges, and the field is the direction of the force on positive charges. But because of this, there's going to be a potential difference, which is going to be negative. So delta V would be positive going to the left, but because you're going to the right, delta V is negative going from left to right. So hopefully that makes sense. Another way to talk about this is imagine you have a waterfall. So water has a certain amount of potential energy at the top of the water, at the top of the hill, waterfall. And then there's different steps that this water is going to flow down, and it's going to lose a little bit of gravitational potential energy in each of these steps. So that's kind of the basic idea behind a series circuit. Okay, now here's a little bit more of the math. All right, so we have 3 resistors and 3 voltmeters, okay? And as we said previously, each resistor gets its own voltage drop, which must add up to the total. So V1 plus V2 plus V3 is equal to VT. So that's what, that's what this number is here, VT. But because of Ohm's law, we know that V is equal to IR. So that means that VT, or total, is equal to IT, RT. And that's what we've plugged in here. And that's equal to I1R1 plus I2R2 plus I3R3. But we make note of the fact that the current is equal through every component in a series circuit, as we discussed previously. So all of these I's cancel out, and we are just left with R in series is equal to R1 plus R2 plus R3. Or another way to say it is that R is in series is the sum of the individual resistances. Now here's another way to think about it. Previously we looked at a resistor as like a little cylinder. And we said that the equation for resistance was equal to resistivity times L over A. Well, what's L? L is the length of the resistor. So if I take one resistor and connect another one in series and connect another one in series, I'm just increasing L. And so as I increase L, I'm going to increase the resistance. And so that makes this formula kind of make sense conceptually, that as I add resistors in series, the total resistance also increases. Okay, so how about an example? Now in these examples, I'm not going to be writing out a lot of calculations because the math is pretty simple. The numbers are just going to pop up. So if you need to, feel free to pause to work through the math yourself. And the first thing we want to do is find the total resistance in this circuit. It's a series circuit. We have a 1 ohm, a 3 ohm, and a 2 ohm resistor. But actually the direction the current's going is through the 2 ohm first, and then the 3, and then the 1. Remember that conventional current goes in the direction from plus terminal of the battery to negative terminal of the battery. So what's the total resistance? It's just going to be 6. 1 plus 2 plus 3. Technically, in order, it would be 2 plus 3 plus 1. Well, what's the current? Well, we use Ohm's law. V equals IR, and V is 12. So 12 is I times 6, so I is 2 amps. And what's the current across each resistor? Again, it's a series circuit, and in a series circuit, 2 amps for each of the resistors. And finally, what's the voltage drop across each resistor? So that would be, for example, V2 would be the voltage drop across the 2 ohm. And it turns out that you just multiply I, which is 2, times R. So the 1 ohm resistor gets 2 times 1, the 3 ohm gets 2 times 3, the 2 ohm gets 2 times 2. So 2 volts, 6 volts, and 4 volts. So if we kind of map that on here, I have 4 volts here, I have 6 volts here, and I have 2 volts here. Lo and behold, if I go through my entire circuit, I have a total voltage of 12. So in series, the individual voltage drops must add up to the total. Okay, and also we can see that because V is equal to IR, if I is constant, as R increases for a resistor, V increases. So the resistor with the largest resistance also has the largest voltage drop. One way to think about this is that the resistance is what converts the electrical potential energy into other forms, and so that's what's happening in this resistor. Okay, what about parallel circuits? So in a parallel circuit, we have multiple loops, and the current splits up in these loops, and the individual loop currents add up to the total current. So that's represented by our equation here, that I total is equal to I1 plus I2 plus I3. Okay? But the other thing to keep in mind is that you can have a junction, and at a junction, the total current going into a junction is equal to the total current coming out. So if you look at my little animated diagram up here, I have a green current, a blue one, and a red one. And I'm not going to try to color code this, but basically I have a green current going this way and then going through this light bulb. I have a blue current going this way and then through this light bulb, and I have a red current going this way and then through this light bulb. So one way to write this is that at this junction, let's call that A, okay? Well, what's going into that junction? I have I red, I have I blue, and I have I green. Those are the currents that are going in. And what's coming out? Well, it's the same thing. I red is up here, I green is right there, and I know my colors. I green is right there, and I blue is right there. So this is the way that things work for a parallel circuit. Okay, now it turns out that in a parallel circuit, you're going to have the same potential difference down each branch of the circuit. One way to think about this, again, with the electric field analogy, is that if you start at this point right here, we'll call that point A, and you end up at this point, point B, you could be going across an electric field right here, or you could be going across an electric field right here. And no matter which way you go, you're going to experience the same drop in potential. Now, how much current there's going to be is going to depend on how much resistance you have. So we'll get to this in a second. And actually where we're going to start with our derivation here is this step, that the total current going into this branch is I1 plus I2 plus I3. So if we had 3 branches. Ohm's law says V equals IR. So I rearrange that to get that I is V over R, and I plug it in. So VT over RT equals V1 over R1, V2 over R2, V3 over R3. And then we use the fact that in parallel, the voltage is the same. Remember CS/VP. Voltage is the same in parallel. So VT, V1, V2, and V3 are all the same thing, and they cancel out. So we get that 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Or 1 over R in parallel is equal to the sum of 1 over R individual. Now, What does this say? This says that the equivalent resistance is always going to be smaller than any individual resistance. Why is that? Okay, well, if you go back to our idea of rho L over A is equal to the resistance. If I put two resistors in parallel that have basically the same area, so this has an area of A, and pretend like I can draw that has an area of A, that's equivalent to basically having one resistor, one really fat one, with an area of 2A. So because as A increases, R decreases, having a greater cross-sectional area reduces the resistance, and in parallel I have less resistance with more branches. It's kind of like lanes of traffic on a highway. The more lanes of traffic you have, the easier it is for cars to flow, and you don't have a lot of resistance to car flow, also known as traffic jams. I'm in Chicago, so we have a lot of that. Okay, so here's an example. We have a parallel circuit here, and we want to find the total resistance. So, because they're in parallel, we apply our equation that 1 over R is 1 over R1 plus 1 over R2 plus 1 over R3. And sometimes the numbers are going to be nice, and sometimes they're not. So in this case, it's not so great, but 1 over R is 0.454, so that means that R is 2.2. Okay, what's the total current? Well, using V equals IR, we can set up that V is equal to I times 2.2. And remember that the total current can be thought of as having our battery of 8 volts connected to one resistor, which is basically RP, the equivalent resistance. So if that's 2.20 ohms, then 3.64 amps is the total current, 3.64. So what's the voltage across each resistor? Well, now the voltage is a constant, it's 8, and it's always equal to I times R, so that means that, well, voltage is just 8, but the current drop is going to be, let me erase this now. Current drop is going to be IR, so that means that I is going to be 8/5, and I'm sorry, it's probably more accurate to say what is the current through each resistor. We really don't want to say current drop, that doesn't really make sense. So what's the current through each resistor? So I5 is 8 over 5, I7 is 8/7, and I9 is 8/9, and we get 1.6, 1.14, and 0.90 amps, and if you add those together, you are going to get 3.64. Okay, so again, I total is equal to I1 plus I2 plus I3. Okay, so if you take anything away from this lesson, you want to remember CSVP, that current is the same in series and voltage is the same in parallel. Next time we're going to be talking about Kirchhoff's loop rules, and we'll also do a little bit with more complex circuits. See you then.